This video is going to be covering Chapter 18, Section 1, which deals with the nature of chemical equilibrium. And we'll start off by looking at reversible reactions. Now, reversible reactions rely on what is known as equilibrium. Basically, equilibrium is when two opposing forces, or in this case, opposing reactions, balance out. Essentially, their effects cancel out one another, and it's as though neither are happening. So in the case of reversible reactions, if you look at the reaction we have here, this is what's known as, a one-way reaction. You take your mercury 2 oxide, and then it decomposes into two atoms of mercury and one molecule of diatomic hydrogen. However, if you were to contain this mercury oxide in some sort of vessel, you'd find that you also get the reaction, where two atoms of mercury and diatomic oxygen will combine to form two molecules of mercury 2 oxide spontaneously. And this is what is known as a reversible reaction, basically, because it can happen either way. And that's denoted with a second arrow going down like that below the first. Now, when you've reached a point where these two reactions, this one up here decomposing and this one synthesizing mercury oxide, are at the same rate, you've reached what is known as chemical equilibrium. And chemical equilibrium essentially means that you're going to have a constant concentration of each of these different compounds, the mercury, the oxygen, and the mercury oxide. But these reactions are going to be going back and forth at a rate such that the molecules themselves will constantly be changing what compound they form. What you'll find is that most reactions turn out to be reversible reactions. However, some will favor the products or reactants over the other. And that's because in reactions such as this reaction of sulfur dioxide with oxygen to form sulfur trioxide, that the reactants realistically react almost completely before an equilibrium is reached. And that's what is called the products being favored. So in other words, this side is being favored. So it's said to lie to the right. This reaction is said to lie to the right. Similarly, if the reactants were only to react for a short time before reaching equilibrium, they would be said to lie to the left. And we denote which side the reaction lies, or which products or reactants are favored, by showing the length of an arrow. So because this lies to the right, we have the longer arrow on top and a shorter one on bottom. Now when neither is really favored, in other words, they happen at about the same rate, you use the arrow I used in the first reaction as a demonstration, where the two are congruent. And the extent to which one is favored over the other, or vice versa, is given by what is known as the equilibrium constant, which we'll discuss later. Moving on now, we're going to be looking at something known as the equilibrium expression, and we'll start by analyzing this sort of generic reversible reaction we have here. So you have, your reactants A and B, which react to form products C and D. Now initially, A and B will have the higher reaction rate. However, as you react A and B to create C and D, naturally, because you have more C and D, those will react more to form A and B. And because these are reacting so much, you'll have less, and it'll slowly decrease the reaction rate. Here you can have it plotted, reaction rate versus time. You can see initially you have a very high reaction rate for A and B. However, as you lose concentration of A and B, that reaction rate slows down. Likewise, as you create C and D from A and B, you'll increase the reaction rate of reactants into products. Eventually, you'll reach the point where the reactions forward, in other words A and B, and the reactions backwards, C and D, reach the same weight. And this is the chemical equilibrium point that we've discussed before. Now, it should be noted that at this point, the reactions don't stop. It just happens that A and B is reacting at the same speed as C and D. However, the concentrations of each, so the concentration of A, the concentration of B, the concentration of C, and the concentration of D are all, that's a D, sorry, are all essentially constant, because you're turning B into D, or A and B into C and D, as fast as you're turning them back into A and B. Now, because at this equilibrium point, the concentrations of A, B, C, and D are all constant, we can make a ratio out of them that will remain constant at all points. So if we have, the concentration of C, the concentration of D, the concentration of A, and the concentration of B, we can create a ratio. In other words, the ratio of the products to the reactants. Now, we have to keep in mind that there isn't necessarily a one-to-one correspondence between, say, C and A. That's what these chemical coefficients are for. So, in order to form this chemical equilibrium constant, with this K, which is what it's known as, you have to raise each of their concentrations to their respective coefficient. So in other words, C is raised to the X, D raised to the Y, A raised to the N, and B raised to the M. Now this K, that is the equilibrium constant, is something that remains the same throughout the entire reaction. It's not going to be changing with the concentrations because these concentration correspondence dictate how this K changes. Now, a few things about this K. First of all, K is determined experimentally. In other words, you can't theoretically calculate K for a reaction. You have to determine it from experimentation. Next, we're going to discuss, what various sizes of K mean. So if you have a large K, it means that you have a very high concentration of products. In other words, you're converting, in this reversible reaction, you're converting most of your reactants into products. So a high K means a high number of products. Likewise, a low K means a low number of products. So you can see here, a low K would be if the denominator were large, meaning there were lots of reactants. So you can see how this ratio and how large K is determines the concentration of products versus reactants. So just show a little implementation of the equilibrium constant. We're going to look at a system we previously looked at, which is the formation of hydrogen iodide from hydrogen and iodine elemental molecules, essentially. So, if we look, we remember that K is the concentration of the products, so in this case hydrogen iodide, raised to its coefficient. So this 2 comes up here, and you square the concentration of hydrogen iodide, and then you also have, your products, or your reactants rather, on the bottom. So this is what the equilibrium constant, once it's all done reacting back and forth, would look like for this system of reactions. And from here you can see it's very easy to determine the concentration of a certain reactant or product if you know the K value. So for example, if you wanted to know how much hydrogen iodide, or the concentration of hydrogen iodide rather, you'd be forming in this reaction at a given temperature, you could simply solve for the hydrogen iodide, that is, bring, the iodine and the hydrogen up here through basic algebra and then take the square root, and you'd get that the concentration of hydrogen iodide is the root of your equilibrium constant times your concentration of iodine and your concentration of hydrogen. So given 1500 Kelvin and that we're at chemical equilibrium and we're given these concentrations, basically when we want to solve for the K value, right? So we know that nitrogen and oxygen will combine to form nitrous oxide through this reaction here. Now all we have to do is, basically plug and chug our equation for the equilibrium constant. So we know that it's the products, so the concentration of nitrous oxide, raised to the coefficient. So in this case the coefficient is 2, so you raise it to the second power over the concentration of reactants raised to their coefficients. Now because both have a coefficient of 1, we just leave them without a coefficient, or without a power above them rather, because they're basically both 1. Now solving for that, you just essentially plug and chug 1.1 times 10 to the minus fifth, because this is all given in the question, 6.4 times 10 to the negative third, and 1.7 times 10 to the negative third. Now, plugging all that in, you get an answer that the equilibrium constant is 1.1 times 10 to the negative fifth. And this is unitless because it's just a universal constant used for measuring. It's essentially like a constant of proportionality.